All right, good afternoon, everybody. I hope everyone's doing well. So a couple reminders before we get started. Today your Lab 5 is due, and hopefully you guys were in recitation yesterday and got your quizzes back. If you didn't, then you can pick them up from Sally Lee, who's in the 8th floor of the Gates building in Stata. And I put up an announcement just letting you know that if anyone feels they need a regrade, then please post the relevant information on Piazza. And you have, normally we give 1 week for this, but because of spring break, you have until 2 weeks from yesterday to do that. All right, let's get started. So today we're actually going to learn how to build our RISC-V processor. So how do we do that? So you might remember this picture from our first lecture. And so we talked about the main pieces that make up a processor. So we've got our register file, we have our main memory, and we have our ALU. And we said that we have ALU operations which can read operands from the register file, perform some operation, and return a value that gets written to the register file. We have load and store operations which allow us to communicate between the main memory and the register file. And then we also have some control flow instructions which allow us to execute instructions not sequentially. So in order to support that, there's actually one more register which we haven't talked about until today, which is called the PC, or the program counter. And what it does is it basically points to the location in memory that is the next instruction that you're going to execute. So if you're going to change your control flow so that the next instruction is not the one immediately after, then you're going to have to update this register to point to the correct location so that you can then go and fetch the right instruction. Okay, so given that, let's think about what are the various steps that we need to follow in order to actually process an instruction, okay? So the first thing that we're going to do is we're going to fetch the instruction that the program counter, or the PC, is pointing to from our memory. Okay? Now, once we've fetched it, we need to actually understand what it's telling us to do. And so we're going to decode this instruction in order to extract all the relevant fields from the instruction. Once we've done that, we actually know what instruction we need to execute. So we're going to go ahead and execute it. Generally, that might mean that we're using our ALU and performing some operation. In the case of loads and stores, we're going to initiate accesses to our main memory. And finally, as the last step, we update our state. And so this is where we would update the register file and the PC with the next value that they should have for the next cycle. So the way we're going to go about learning this is we're going to start off by talking about all of the major components that are necessary in order to build this processor. And so this includes the register file, the ALU, the memory, the decoder, the execution unit. We're going to go through each one of those one by one today. And then what we're going to do is we're going to put it all together in order to actually implement a single cycle RISC-V processor. And hopefully we'll get to the end of that by the end of lecture today. And then next time we're going to look at how we can also make this processor be a multi-cycle, non-pipelined implementation. And we'll learn why you might want to consider that in the next lecture. Okay, so we'll start with the ALU, which we're all very familiar with at this point. Basically, this looks exactly like you expect. You have two operands, A and B. You have a function specifier, which tells you which function the ALU should perform. And then based on those three inputs, you produce the result. And so we have a function that is defined, which is called the ALU, and it does exactly that. So it takes two inputs, A and B, each of which are defined to be here of type word, which is basically just a 32-bit value. and we also pass the ALU function, which is the function that we want to perform, and it returns a word or a 32-bit value, which is the result of having performed that ALU operation. And so the ALU operation is defined using this enumerated type, which lists out every single one of the ALU operations that the RISC-V supports. And so, you should at this point be, familiar with this, because this is what we've built in Lab 4. Okay? And so now we're going to move on to the next step beyond building the ALU. So in addition to the basic ALU, which has instructions for computation like add and subtract, it has some instructions for doing shifting and things like that, we also have another portion of our ALU. We call this the branch ALU, or the ALU branch. And what it does is it basically does a comparison between two registers and produces a Boolean value, which is going to tell you whether or not you're taking your branch. And so the inputs to this ALU are A and B, which are two 32-bit values, and then the branch function, which is going to say what kind of comparison do I want to do between these two registers, and then it's going to return a bool, which is going to tell you, am I taking the branch or not? And so this branch function is also defined as an enumerated type with all the different types of branch comparisons that the RISC-V supports. And so specifically this is equal, not equal, less than unsigned, and so on. Okay? And so together, the ALU and the ALU branch will allow us to do all of the ALU operations that are necessary for our processor. And so we're now going to go ahead and take a look at what does the function implementation of this ALU branch look like. And so as we mentioned, it takes as inputs A and B and the branch function, and it returns a Boolean. And it's really a very basic function where all it's doing is it's a case statement that takes a look at the branch function, and for each one of the options that branch function can be, it performs the appropriate comparison between the two registers. So if the branch function is equal, it checks whether they're equal. If the branch function is less than, it checks whether A is less than B, and so on and so forth. And it returns a Boolean value, which is assigned to this branch taken variable, and then that's what we return from this function. Any questions about that? Great. Okay, so we're done with the ALU now. Now we're going to move on to the register file. So the register file is a module that has 3 ports, okay? We're going to have 2 read ports and 1 write port. What that means is that we can do 2 reads and a write all in the same cycle, okay? And so that's going to allow us to do things like, ALU operations that need to read 2 source operands and write to a destination operand all in the same cycle. And so what does this module look like? So it's got these 3 methods for reading the 2 ports and for writing. And recall that registers can always be written to or read from. And so by default, their guard is always true, and so we're not actually going to show it in the illustration here. And here's the interface definition of our register file. So first we have a couple type defs. The word one you've seen before. We're going to start more and more just using word to mean our 32-bit value that we're either accessing from a register, from memory, and so on. And then we also define this R index, which is a 5-bit value, and we're using 5-bit values in order to specify which of the 32 registers we're trying to access. Okay, so it's the index into the register file. And then we have the 3 methods that we just mentioned. So the first is RD1, which reads from port 1 of the register file, and it receives an index which tells it which port to read. it returns a word, which is the value of that register. RD2 works exactly the same way. And then the write method is an action method, which is actually going to modify state. And what it's going to do is it's going to take the data that's passed to the write method and write it to the register whose index is index. Okay? All right, so what does the register file implementation look like? Well, we've got a module for this register file, and the first thing we need to do is we need to instantiate the state. Okay, and so what we're going to do is we're going to define a vector of 32 registers, each of which is of size word or of size 32 bits. Okay, and then we're going to use this function called replicate m, which you might recall that you saw in lab 5. And what this replicate m does is it basically says, give me 32 registers. Otherwise, if I just called make reg 0 here by itself, all 32 elements in this vector would point to the same single register, okay? And so this tells me, give me actually 32 different registers, and you use this a little bit in your completion buffer in lab 5. Okay, and then we said that we have the 3 methods for a register file. So the first 2 are pretty simple. You're just going to be reading from the register file. And so all you're doing is you're passing in an index, and what it returns is the element from that 32 element vector whose index is our index. Okay, so pretty clear how we read the 2 ports. And then the write is pretty similar, except that, so we're going to do what you expect, which is take the data field that's being given to us and update the register file pointed to by index with that value. But there's one additional thing to note here, which is this check over here. So we're checking that index is not equal to 0. Why do we do that? Yep.
Because the 0 register is only used for 0.
Exactly, okay? And so in the case that our destination register is the 0 register, then we're actually not writing to the register file, okay? And so that's what that check does for us. Now, if you recall from our conflict matrices that we saw last time, we saw that it's possible to do both reads and writes from our register file at the same time. And so the implication of doing, 2 reads and a write, though, is that it always behaves as if the reads happened before the write. So if, for example, I am reading and writing to the same register, I'm going to first read the old value, and then I'm going to write the new value that I just produced at the end of the cycle. Okay, any questions about the register file before we move on to the memory? Great. Okay, so today we're going to look at what we call a magic memory module. And we call this magic because it's not really how memories work. But for just today's lecture, we're going to use this as a model. And then in future lectures, we're going to talk about a more realistic memory model. But what this magic memory model assumes is that the memory behaves just like a register file in the sense that you can do combinational reads, and if you do a write to this register file, it's going to happen on the next rising edge of the clock. Now in reality, when you look at SRAM, which stands for static random access memory, and DRAM, which is dynamic, what happens is that these memories are actually very slow. And so it's not realistic to assume that you're going to be able to access this memory in a single clock cycle. And so we're going to be dealing with that complication later on. But for today's lecture, let's assume that it is, and that we can access it very quickly, just like we can access our register file. Now the only difference, though, between this magic memory and our register file is that it's got a single port in order to access it. So we can't do a load and a store at the same time. We can only do one of them. And I just said that we'll talk about more realistic memories next time. So what does the interface for this magic memory look like? Well, it's basically got one method, which is a request method, and depending on what we're trying to do, we're going to send, we're always going to send an operation which says, do I want to do a load or do I want to do a store? If it's a load operation, then I'm going to send an address which is going to tell me where I want to read from in memory, and then the result of that read is going to come back on this load data wire. If I'm doing a store, then I'm going to send the address that I want to write to, as well as the data that I want to write to that location, and I'm going to have to set enable to true in order to update that location in my main memory. Okay, so once again, we're assuming here that you can always read and write from main memory, and so the guard is always going to be true, and so we're not showing it here. And the details of the interface look like this. And so basically we're just defining a single action value method which takes in a memory request. So what's a memory request? A memory request is defined right here as this special structure which consists of 3 pieces of information. So what do I need in order to actually perform a memory request? I need to say, am I doing a load or a store? So that's my operation. I need to provide the address of the location in memory that I'm trying to access. And in the case of a store, I need to also provide the data that I want to write to that memory location. And so this struct basically just lumps these 3 values which are related to a single memory operation into a single data structure. And this memory op itself is also another enumerated type which can just take on the values of load or store. So how would I use these methods? So suppose that I have instantiated a memory module that's called M. I would call the request method on M with one of these memory request values. And so suppose, if I said op was load and my address is A, then in that case data doesn't have any meaning, so what we're going to do is we're going to set it to a default value. We call here DWV stands for default word value, which is basically just going to be 0, but we want to show that it's actually just a default value which could have really been set to something else if you wanted to. All right, and so when we do a load, it's going to return the value that it reads. Yes?
For the enable, right, is it automatically set true or false depending on load and store, or do we have to encode it for the enable?
You have to, it's not that you have to encode it, you have to specify when it is that a write should happen, and by specifying that in your rules, that will produce the correct enable.
Okay, thanks.
Any other questions? Okay. So the load is going to return the value from memory, and we can assign that to this data variable right here. Now suppose instead that I wanted to do a store. What would that look like? Well, very similar. The only difference is I changed my operation to be a store instead of a load. And this time, I actually have to provide real data, which is what I'm going to write to that memory location. And so this V corresponds to the actual data that I want to write. And notice that in this case, we're not actually getting anything back from our memory in our store operation. So what we do is we take that the value from the action value and just assign it to a dummy variable because it doesn't actually mean anything to us. Okay? So this just illustrates how we perform loads and stores on our magic memory. Is that clear to everybody? Great. All right. So now we get to the more interesting stuff, instruction decoding. So how are we going to figure out what instruction we want to perform, and when we read these 32 bits that the program counter is pointing to, what does it even mean? Okay? So what we're going to do is we're going to fetch this instruction, and we're going to actually interpret what each one of the fields is telling us. And so the kinds of things that we need to extract from our instruction are, what ALU operation I want to do, what are my source registers, what's my destination register. If there's a constant encoded into the instruction, then I need to be able to extract that, and so on. Now, note that not every single 32-bit permutation is actually going to produce a valid instruction. So when we're decoding our instructions, not only do we need to deal with instructions that are actually valid, but we also need to identify the ones that are invalid and deal with them appropriately. And finally, you also notice that, you know, in the definitions of these instructions, a lot of the instructions are very, very similar to each other, and they only differ slightly both in their implementation as well as their encoding. And so you just want to make sure that you're very careful about precisely identifying what each encoding represents. Now, in the case of RISC-V, because it's a reduced instruction set computer, one of its features is that its instruction set is pretty simple. And so that actually makes the job of decoding be much, much easier than if you take an instruction set like the x86 that has, you know, tons of different options, and that basically makes our decoding process so much harder to do than it's going to be for us with a RISC-V. Okay, so how are we going to interpret what these 32 bits of an instruction mean? Okay, so I give you these, you know, 32 bits here, and I want you to try to figure out what instruction this represents. So what's the process of doing that? Well, first of all, you're going to use your handy-dandy reference manual, and it's going to tell you that in all of the RISC-V instructions, the bottom 7 bits are what we call the opcode. So the opcode is basically telling you what kind of an instruction it is. And so in this example, this opcode is telling us that it's of type op, and we'll define what that means in a second. And it uses the R-type encoding. Okay, so once we know that, then I know how to figure out what the rest of the bits in my instruction mean. Okay, so specifically, because it's an R-type encoding, I know that these bits over here refer to the destination register, these refer to RS1, these refer to RS2, and so on. Okay, so once I know what bits represent what, then I can go ahead and extract those fields from my instruction. And so I find that my function in this particular example is just 0, 0, 0, which corresponds to the function add. The registers are just an index into my register file, so they're going to be a number between 0 and 31, which tells us which register we're accessing for each of these 3 register fields. And so we've got a destination register that's x3, a source 1 that's x2, and a source 2 that's x1 in this particular example. So what is this instruction actually doing? If we take a look at the functions that we've defined so far, it's going to actually call a few of them. Okay, so the first thing is it's doing a write. So we're going to call the register file write function, and that function needs 2 inputs. It needs an index, which is the register you're writing to, and so the register we're writing to in this case is register 3, and it needs the value that you're going to write to it. So how do we figure out what that value is? Well, in order to figure out what that value is, we have to perform an ALU function. And so we're going to perform an ALU function using our 2 source operands and the function that we figured out that is encoded into this instruction. Okay? And in order to get our source operands, we need to call yet another method, which is the read methods from our register file. So this says read register 2, read register 1. The values of those 2 registers are your source operands. Add them in the ALU, and the result of that is what you're going to write into register 3. Okay? Now, in addition to doing all that, there's one more very important thing we have to do, which is we have to prepare our processor to execute the next instruction on the next cycle. Okay, so if I'm doing an add instruction, then what do I want my next instruction to be? Store, you said? It's not a store. The add actually writes to the register file directly. You don't need a store instruction. And remember that a store instruction actually writes to your memory, so you don't want to perform a store. But what do we want to do right after the add? We just want to execute, yep.
Increase the program count.
Yeah, we just want to execute the next sequential instruction because unless we have some kind of control flow instruction, we just execute instructions in order. And so recall that instructions are 4 bytes wide, and so in order to point to the next instruction, I need to increment my program counter by 4. And so we see here that the second piece of what this instruction does is that it also increments the program counter so that for the next cycle we'll be pointing to the next instruction in our memory. Any questions about that? Great. Okay. So we talked about, we have a whole bunch of ALU instructions, and this is the full list of them. And if you take a look at their descriptions, you'll see that they're all really pretty much the same except for this field right here, which specifies the ALU function, okay? And so what that allows us to do is basically lump all of these ALU 2-register instructions into a single category. And this is what we call the op category. So op means that you're doing a 2-register ALU operation. All of those types of instructions are going to be encoded in exactly the same way. And the opcode is going to tell us that that's the kind of instruction that it is, and then we're going to be able to extract the rest of the fields, which are the ALU function, the 2 source register indices, and the destination index. Okay? All right. Next come our ALU instructions with immediate, okay? Once again, if we take a look at the definition of these instructions, we see that they all look exactly the same in that they have a destination register, a source 1, an immediate value, and all you're doing is a different function on those 2 sources to produce your output. Okay, and so these instructions too can be lumped into one category, all of which are going to be encoded in exactly the same way. And this category we call op immediate to indicate that one of our source operands is an immediate value rather than the second register. And so once again, the fields that are going to be encoded in these types of instructions is the ALU function that you want to perform, the destination register, the source 1 register, and then there is no source 2. Instead, we're going to extract an immediate value, which is a constant that's encoded in the instruction directly, which is going to be our second operand for these types of instructions. Okay, so that doesn't seem so hard, right? But in some cases, decoding can actually be pretty complicated. And so we're going to take a look at this example to see, when does that happen? So we're going to start off exactly the same way we started with our ALU instructions and look at the bottom 7 bits, which specify our opcode, okay? And if we look at our reference manual, it tells us that this particular opcode refers to a branch type of instruction. And we know that branch type of instructions follow this, what we call B-type encoding. And I'll show that to you in just a moment. So from that, we know how to interpret the rest of our bits. And so we'll start with the easy parts, which is these bits refer to the function that's going to be performed, and then we've got our RS1 and RS2, okay? So the function of 1 in the case of branch instructions means that the branch instruction that we're trying to perform is a branch not equal. So we're going to take our 2 source operands, we're going to check if they're not equal to each other, then we will perform the branch. Otherwise, we won't perform the branch. Now, in order to determine the destination of our branch, we have to extract an immediate from our instruction. And the immediate is actually stored in a very convoluted manner in these branch instructions, okay? So you have to very carefully follow the reference manual, which tells you, that bit 12 of your immediate lives over here, bit 11 lives over here, 10 to 5 come from over here, and so on and so forth. And so we're going to put all of those bits together in order to make our 12-bit immediate constant. And the assumption in branch instructions is that bit 0 is always 0. And then in addition, we have to take these, this constant that was encoded in our instruction and turn it into a 32-bit value. The way that we do that is by sign extending. So what do we have here? We have here a bunch of 1s followed by 2 zeros. So if I sign extend that to 32 bits, what am I going to get? Again, a whole bunch of 1s followed by 2 zeros. Okay? It's just going to be 32 bits long instead of 12. And what does that number represent? That represents a -4 in 2's complement. So what does this tell me? This tells me that when I do my comparison operation using my branch ALU, so I'm going to, let's take it step by step. First thing I'm going to do is, once I've figured out what my indices for my source registers are, I'm going to read their values from the register file. I can then pass those two values to the branch ALU function together with the type of comparison that I want to do. And that's going to return a Boolean, right? If they are not equal, it'll return true. If they are equal, it'll return false. So if they are not equal, then I want to take the branch. So what does it mean to take the branch? It means that this time I'm going to change my PC to be PC plus this immediate value, which happened to be -4 in this example, and that's the address of the instruction that I actually want to jump to. Whereas if I'm not taking the branch, then I do what I always do, which is just set PC to PC plus 4. Questions about that? Terrific. Okay, and so here's the list of all of our branch instructions, and once again they're all very similar except for the branch function, which is the comparison function that they're using. And so these instructions also are all encoded as one category. We call this the branch category, and the fields that are encoded for branch instructions are the branch function, the 2 source register indices, and then an immediate value, which is going to tell us where to go to in the case that we do take the branch. All right, so we're almost there. These are the 5 remaining instructions. And these 5 instructions don't actually match any kind of pattern with other ones. And so we actually treat each one of these as its own category. Okay? So these are the 2 unconditional jump instructions, the load upper immediate, and our load and store instructions. Okay, and so those are going to each have their own opcode, and we'll deal with them in a separate case. In addition, when we do loads and stores, we also have to produce an address that we're going to use in order to access our main memory. And so in addition to producing, data like that you would in the ALU, in the case of loads and stores, what your ALU is going to be doing is actually producing the address that you're going to feed to memory, and then you're going to be able to perform your memory operation. Okay, so let's review what is it that our instruction decoder needs to do. So we need to define a function that's going to be able to extract all of these different fields that we've been talking about from our instruction. So what are the fields that we've identified? The first field is the type of instruction, right? And so we've identified that we have an op immediate, branch category, and then the rest of our 5 special instructions. And then we add one more, which is unsupported. So when do I want to use unsupported? If I happen to come across some encoding where the opcode doesn't correspond to any of the valid encodings that I have, then we're going to mark that as an unsupported instruction, and we'll have to deal with it accordingly. Then we're also going to be able to extract, we need to extract our ALU function, our branch function, our source and destination registers, and finally the appropriate immediate value depending on what kind of instruction it is. And you'll notice here that there are actually all sorts of immediate values and different encodings for them that are specified here. We label each one of them like immediate I is one type of encoding, immediate B is another type of encoding. You also notice that some of these are 12-bit constants, whereas others are 20-bit constants. And in all cases, we're going to extend that constant that was encoded into our instruction to a 32-bit value. Oh, also it's important to notice that none of these instructions have all of the fields, okay? And so we need to make sure that we're dealing properly with ignoring fields that aren't relevant for a particular instruction. Like, for example, if I'm doing a store instruction which doesn't write to the register file, I want to make sure that, I'm not writing to whatever value the destination field happens to have in it. Okay, so I just wanted to show you a couple things from the reference manual just to make this all a little bit more concrete. And so the first is the different types of immediate encodings. And so this shows us that we have basically 6 different immediate encodings, and it shows you exactly which bit corresponds to which portion of your immediate depending on the type that you have. The second thing that I wanted to point out is here's just a portion of the instruction encodings. And so if you take a look at, groupings of these encodings, like all of our branch instructions here, they all have the same opcode, as we've mentioned, and they all have the same type of encoding. Okay, so this is the function, this is RS1, this is RS2, and so on. If you look at the ALU immediate instructions, the same thing holds true. It's got a shared encoding, and here we see a destination register, a function, an RS1, and an immediate, okay? So depending on which kind of instruction it is, you're going to interpret those bits differently, and you're going to use those fields that you extract from your decoding function. So what are all the fields that our decode function needs to extract? It's basically what we've been talking about. So we've got the instruction type, the ALU function, the branch function, the destination and source registers, and an immediate value. And we call this structure a decoded instruction type. So these are the field names of a decoded instruction, and what's shown here on the left are the types of each of those field names. So let's take a look at what, how these types are defined. So a bunch of these are enumerated types that we've already seen. So specifically, we've got here the instruction type is, any one of these categories that we just saw. An ALU function we know is one of these types of ALU functions listed in this enumerate. Branch function can be equal, not equal, so on and so forth. Now, one thing that's new here is this rdest. Okay, so rdest is a new type of structure that we're defining, which is going to specify what our destination register is, but it needs to have 2 pieces of information. Not only does it need to have the index of the destination register, but it needs to also tell us, is the destination register valid? Okay, and so what we're going to use this valid bit for is to tell us when we should not be writing to the register file. So if the valid bit is 0 saying it's invalid, then that means that we should not actually be updating the register file in that situation. Okay, and so if you happen to have, a destination register that's 0 and it's valid, that's still going to be treated like an invalid destination. And in the case of an invalid destination, what it means is that we don't write to the register file. And so this decode instruction is what you're going to be writing as your lab 6, okay? This is the main piece that you're going to be writing, and most of the rest of it we're going to be giving to you, and we're going to tie it all together. So in the rest of the lecture, let's try to now put all of this together and see what some of the other pieces that we're giving to you look like in order to actually create this entire processor. So what we're going to do is we're going to define a make processor module, and you'll notice that the interface that we've specified here is empty, and what that means is that there are no methods associated with this module, okay? So what does this module do? This module represents your actual processor. So the first thing that we need to do is we need to instantiate our state. So what state do we have in our processor? Well, we said we have a special register, which is the program counter. We have our register file, and we have our memory. And we've broken up our memory into 2 separate memories, one for instructions and one for data. Okay? And so we instantiate all 4 of these pieces. And then we have a rule which tells us, which actually does the processing of our instructions. So as we said at the beginning of class, what do you need to do in order to process an instruction? The first thing you need to do is you need to fetch that instruction from your instruction memory. Okay, so we're going to perform an instruction memory request where the type of request is a load, and the address that we're trying to fetch from is the value of the PC, and this is just our dummy value when the data field doesn't matter. Okay, so we get the instruction by performing this iMemory request. Once we have that instruction, then we can call the decode function, which you're going to be writing in Lab 6, so we're not going to show the details of that today. And so the decode instruction is going to return something of type, decode instruction with all of those fields that we just showed in the decode instruction structure. Once you've got, and so that consists, of things like the instruction type, the function type, and so on. Once you've got the decoded instruction, then you know what your source registers are, and so you can then go ahead and execute your register file reads for your source 1 and source 2. And now you're ready to execute. Okay, so your execute function is going to take the values of the source operands together with a decoded instruction and the PC, and it's going to actually figure out what we're trying to update our state with. And finally, it's going to produce what we call an E instruction, which is yet another data structure that's got all of these fields in it. And then the last step is going to be to actually update our state. Now notice that these green comments here are in many cases indicative of actually missing code, okay? And so we're just kind of showing you a block diagram of what this code looks like, but in the Lab 6 code you will actually be given this entire function, and what you will be writing is the decode. So we'll see what it means to update the state in just a moment. So let's first see what the execute function looks like. So the execute function is going to take the decoded instruction, and it's going to take the 2 values that you read from your register file, meaning your 2 source operands, and depending on the instruction type, it's going to produce different results. So let's see what it does. So the first thing we're going to do is we're going to extract the fields from our decoded instruction, and then we're going to, the goal of execute is to produce an E instruction structure. So we're going to initialize the fields that are in this E instruction, which are data, next PC, and address, to this default word value. And now our function is going to actually set these to appropriate values when that field is relevant to the type of instruction that you're executing. Okay? So let's take a look at op-type instructions. So what do op-type instructions do? Op-type instructions are going to take our two source values, and they're going to call the ALU function using the ALU func, which you extract from your decoded instruction. And the result of calling this ALU function is going to produce this data field of our E instruction, which stands for executed instruction. Okay, so that's the result that the ALU produced. The second field that we need to update in our executed instruction in the case of an op instruction is next PC. And so in the case of an op instruction, which is just a 2-register ALU operation, we said that the next PC should just become PC plus 4. Okay? And so that's what that case is going to deal with. And so similarly, we can take a look at the other ones. What's an op immediate going to look like? It's pretty much the same thing, except that now our second operand, instead of being our val2, is the immediate value that we extracted from our instruction. How about a branch? A branch, instead of using the regular ALU, it's going to use the ALU branch. It's going to use these two values and the branch function to determine, am I taking the branch or not? So this ALU branch is going to return a Boolean. If the Boolean is true, meaning I am going to take the branch, then my next PC is going to be determined by the value of PC plus my immediate. If I don't take the branch, then PC just becomes PC plus 4. So notice that in the case of branch, I've only needed to specify what next PC is. I didn't have to specify what data is because there is no data being returned in the case of a branch instruction. All right, how about load up or immediate? Load up or immediate just says take this immediate and make that be your data, and then your next PC is your next instruction. These are jump instructions. So these are unconditional jumps. So what do these unconditional jumps do? Remember that they're jump and link instructions. Okay, so the and link says take the value of PC plus 4, which points to the next instruction, and store it in your destination register. Okay, and so the data that we're going to store into our register file in the case of these unconditional jumps is the PC plus 4 value. That's what's going to go into one of our registers. The next thing we have to do is figure out what next PC is. So in the case of the jump and link, our PC is determined by adding the immediate constant that was in our instruction to our current PC. Whereas in the case of jump and link register, we're not actually using the PC value at all. We're just jumping to the value that's stored in a register after we've added this immediate to it. And there's yet this additional complication, which is that we AND it with this tilde1, which basically means that we're zeroing out the bottom bit. In reality, in our subset for 6004 of the RISC-V, we're only ever dealing with word boundaries. So in our situations, the bottom 2 bits are actually always going to be 0. But this is a general RISC-V handling, which can also do things like half-word instructions, which we're not supporting, and so that's why it's only zeroing out the bottom bit. In any case, not something you need to worry about too much. Finally, we've got our load and store, and so what our load does is it needs to actually produce the address that we need to feed to our memory. And so the address is produced by taking the value of register 1, adding the immediate to it, and then in this case PC again just becomes PC plus 4. And store is very similar, except that for store we also have a data which comes from our second source register, and that's the value that we're going to write to our memory. Okay? And so once we've figured all of this out, then we basically can fill in this EINS data structure, which now tells us all the different pieces of information that we need to know depending on what kind of an instruction we were trying to execute. Okay? So we're almost done. The last step, so let's review. What have we done? First, we fetched our instruction. Then we decoded it. Then we read our source operands from the register file. Then we executed the operation that we wanted to execute. And now, finally, we're going to update our state, okay? So what do we need to do to update our state? Well, we're going to look at these fields that came out of this executed instruction. And we can extract the data field, which is basically, you know, the result you got from your ALU or whatever it is for the appropriate instruction. And what we're going to do is we're going to determine whether or not we're going to do a register write. A register file write. And so this is where, answers your question with regards to the enable for the register file. What we're going to do here is we're going to check, is the destination index that I've been given, right? Remember, it's a special structure that we defined, which consists of both an index and a valid bit. So I only want to write to my register file if that valid bit is true. So what I need to do is I first check the valid bit, and only if it's valid do I actually call this register file write. And what I'm writing to in that situation is the index of my destination register and the data that I produced from my executed instruction. In addition to writing to the register file, we need to update the PC. And so we determined in our execute instruction what the next PC is going to be on every single different kind of instruction. And so we simply set PC to be this next PC. And finally, we have our memory accesses. So in the case of a load, now we're going to access our data memory. We're going to do a data memory request that's of type load, where you send it the address that you computed in the execute, and then that becomes the address of the location you're trying to load from. And the value that it returns becomes your data, which you're then going to potentially write into your register file down here. And finally, there's a store operation. And so in the case of a store operation, we once again do a memory request with a type store, and in this case, your address and data are the values that you figured out in your execute function. And so that basically summarizes it all. In the next slide, we just give you a kind of cool blue spec thing that you can do, where instead of just inlining this code, you could have actually defined an action function. I'll let you guys take a look at that yourselves. And finally, this is the complete picture of what we've built, okay? And so all of these arrows that are connecting these various pieces that we've been talking about are automatically generated from your blue spec specifications. And you're going to build this big piece right here, and we're going to tie all of these together in order to have an actual working single cycle RISC-V processor, and then eventually we're actually going to build even more complicated versions of this processor. All right, sorry for going over a tiny bit. Here's your take-home problem, and we'll see you next time.